Whoa. What is that? I have this word called implicit differentiation. Okay, so we've been a little bit spoiled here. And this is something that's going to be new, like brand new. But our spoiledness has been that our y's have always been by themselves. It's always been y equals, f of x equals, g of x equals. And I want to find the derivative. I want to find dy dx. But then the question comes is, well, what happens when y is not always by itself? What happens if I have something that has like this x cubed plus y cubed minus 9xy equal to 0? And what ends up happening is, hey, because it's a y cubed, I have three distinct functions. And when we remember what a function is, right? A function is something where it doesn't, it passes the vertical line test. And so if you can see here, this part right here, I have three separate solutions, or three separate answers for an x. That's not a function. That's why it's called an implicitly defined function, because I have one function here, two function here, and my third function here. Okay? So each of these are called explicit formulas. All right? And what we're able to do, or we're going to be able to do today, is be able to take the derivative of an implicit function like this without having to get all three of the explicit functions, which is good, because otherwise we'd have to find each of these three functions, and that's not pretty. I'll give you an example, a pretty example. Okay? So here it is. So if I were just to ask you to find the derivative of this, y cubed is equal to 8x squared. Well, your first response might be, well, let's go ahead and let's take and find just y. And so when I do that, I can go ahead and say, well, if I take the cube root of both sides, this is the cube root of 8x squared. And then I don't like to have square roots or cube roots or whatever, so I'm going to go ahead and say that y is equal to the 8x squared to the 1/3. And doing the derivative, I'm going to say I'm going to say dy dx, right? Because I'm going to take the derivative of y with respect to x is equal to, all right, so here's my candy shell, 1/3, 8x squared, keeping that chocolate the same, reduce my power by 1, times 8x squared, derivative of the chocolate would be 16x. Now I want to go ahead and make this to where this is, a nice happy fraction. So I now have 1 on top. I have the 16x's on top. So I have 16x times 1, which is just 16x. And I have a 3 on the bottom, and this mess up here. So it's 3 times 8x squared to the 2/3 power. Okay? And that's how we would take the derivative of it. But what if there's another way? And there is. I don't have to solve for y. What I can do is I can instead say from the very beginning, say, you know what happens if I were just to take the derivative of y cubed? It's okay, we can do that. Okay, if I take the derivative of y cubed, well, I still have 3y squared. Okay? But it's kind of like a little mini chain rule, right? Well, the derivative of my shell was the 3y squared. The derivative of my chocolate was the derivative of just plain old y. The derivative of y in my chocolate, oh, well, that's dy dx, right? That's what we had over here, right? Derivative of y all by itself was dy dx. Okay? So the candy shell was the x cubed or something cubed, so I took the derivative of that and left my chocolate alone. And then I took the derivative of dy dx, or of y, which is dy dx. Okay. And then I take the derivative of this just the same, 16x. Now I'm going to go through here and I'm going to say, well, what do? Well, I want to solve for dyx. That's what they want me to do. They want me to find dy dx. So I go and say find dy dx is equal to 16x over 3y squared. And normally when we take the derivative implicitly, which is what we did right here, we took the derivative implicitly. Over here, this is explicitly. Okay. When we took the derivative implicitly, you might be thinking this is where we would stop. But I want to show you that the two are equal. So what is y squared? Or what is y? Well, we found y over here, right? So let's go ahead and just plug that in. I can say, well, dy dx is equal to 16x over 3 times y. Well, y came out to be 8x squared to the 1/3, and all of that squared. Oh, and then I have a power to the power, which means I multiply. So this is equal to 16 over 3 times 8x squared to the 2/3 power, which is exactly the same thing. So again, look, all of these steps were needed, and all I need for this is here. This is what my answer is going to be, and I'm going to be happy with that. Okay? Here we go. What's next? Alright, so here we go. They said find the slope of the circle x squared plus y squared is equal to 25. Alright. So let's do that. Add the point 3 comma negative 4. So let's do that. We're going to do it implicitly. So I take the derivative of x squared. Well, that's easy enough to do. That's just 2x. Plus, now I'm going to take the derivative of y squared. Again, when it's with y, you got to think of it kind of like a little mini chain rule. Okay? The shell part, I can take the derivative of shell. That'd be 2. Leave the chocolate alone. The y is the chocolate. And now I'm going to take the derivative of the chocolate, derivative of y. Well, that's dy dx is equal to, well, what's the derivative of 25? 0. And now I want to solve for dy dx. And the quick little algebra there, dy dx. Okay, subtract the 2x, divide by 2y, you get negative 2x over a 2y, which is just equal to negative x over y. Well, now what do they want me to do? They want me to find the slope at a particular point. Notice here I have a point 3 comma negative 4. So what they're asking for is to say evaluate dy dx at 3 comma negative 4. Well, when I do that, I just plug in the x's for x's and y's for y's. So I have a negative 3 over a negative 4, which is then equal to a positive 3/4. Now I want to ask myself, hey, does this make sense? Well, let's go find out and take a look at the graph. Okay, well, here comes the graph. Bing. Oh, look, here's the point 3 comma negative 4. Here's my tangent line. Does that look like a positive slope? Yeah, it's a positive slope and a positive 3/4 at that. Kind of cool, right? So we could get really crazy. Let's see if we can get a little crazy. Here's a little crazy. Wow. Okay, so now look, they're asking for us to find the equation of the tangent line at a point 1 comma 1 on the curve, blah. So again, remember, they want us to find the equation. Boom. So as soon as you see that, let's change colors. Okay, you got to be thinking, I need a point. Well, good news, here's a point. Next thing I need is a slope. Slope means I need to find dy dx. Okay, so if I find dy dx, okay, we can go ahead and do that. So dy dx. So again, I start doing this little baby step here. Okay, first part is I take the derivative of y to the 4th. So it's 4 y cubed times derivative of chocolate, derivative of y, dy dx, plus, this is kind of like a product rule now. I now have x and y multiply together, so you got to treat it like a product rule. So leave the first one alone. X, take the derivative of y. Well, the derivative of y is dy dx. And then I want to go ahead and add, okay, take the derivative of x, 1. times y, y, is equal to, take the derivative of this, that's easier to do, 3x squared minus 1. So what do I do? So this is what you're going to do with all of the stuff. Everything with a dy dx in it stays on one side. Everything that does not have a dy dx in it moves over. So I see this does not have a dy dx in it, so I'm going to move it over. And what does have a dy dx in it, I'm going to factor. So I'm going to factor out a dy dx. Factor from there, I end up with a 4y cubed plus, here gets an x, okay, is equal to 3x squared minus a 1, and then minus this y. And I did all that so I can solve for dy dx by dividing by this junk over here. And when I do that, I get dy dx is equal to 3x squared minus a 1 minus a y all over, okay, 4y cubed plus an x. Okay. Now comes the semi-easy part. Now that I found my derivative, that was the hard part. Now I want to go ahead and plug in my point. I want to find dy dx in terms of at 1 comma 1. And I plug in. So this would be 3 minus 1 minus 1 all over 4 plus 1, which is going to be equal to 1/5. So there's my slope. I have my point. So I get y minus 1 is equal to 1/5 x minus 1, and I am done. Ta-da! I think that's kind of cool. All right. Well, let's do what's next. Okay. Show that the slope dy dx is defined at every point on this graph. Woo! Okay. So again, with this one, with everything with a y in it, you want to treat it like a chain rule. So this first one here, it's 2y. Okay. Well, it's going to be take the derivative, so it's 2. Take the derivative of y. What's y? Derivative of y, dy dx is equal to 2x plus derivative sign is cosine of y. Leave whatever in there, and then I'm going to take the derivative of this side times dy dx. So what I'm going to do is go ahead and move everything with a dy dx to one side and factor out the dy dx and then divide. So here we go. I factor out my dy dx and I end up with a 2 minus a cosine of y, which is all equal to 2x. And now I go ahead and divide by that, and I have dy dx is equal to 2x over 2 minus cosine of y. So they ask you to show that the slope is defined at every point. So in order for it to be defined, okay, here's my slope, defined at every point. So I have to think to myself, what makes something defined? What makes this function defined? When does this equal 0? Because if the denominator equals 0, then it's not defined. So if I go ahead and do that, where I do 2 minus a cosine of y is equal to 0, and I come over here and I say, well, that's going to happen when 2 is equal to a positive cosine of y. But can that happen? Can cosine of y ever equal 2? No. Cosine is, the most it could be is 1. And since cosine of y will never equal 2, will not equal 2 for any value of y, dy dx is defined everywhere. Okay? That's the justification for it. All right. Now this one here, woo, that one's hard, that one's long. Okay, I don't want to mess with this one. If you guys want in class on the next day we see you, we'll deal with this, but not right now. Okay? It's going to take too long and the video will be way too long. So we'll deal with this on the next time I see you. All right? All right, so now this one I do want to do is my last example before you get to the homework. So what I want to do is I want to say it wants to do the second derivative. That's what this is. d2y over dx2 is saying I want to find the second derivative. Okay, so this takes a little bit. So first thing we have to do is find the first derivative, then we find the second derivative. So I'm finding the first derivative. Again, take this one normal. So this would be a 6x squared. Now I get to a y. So now I have to be cautious with it and treat it like a chain rule and be 6y and to the first power, and then take the derivative of the chocolate, which is times dy dx, which is then equal to derivative of 8, which is 0. Again, I solve for dy dx, and what I get here is I get dy dx is equal to a negative 6x squared over a negative 6y, which is then just equal to an x squared over a y. Last part of this is now I want to find the second derivative. Well, I'm finding the second derivative. This is where I got to start off by saying it's going to be low d high, high d low. Okay, all over low squared, right? So low d high, y, times derivative of high, 2x, minus high d low, x squared, times, what's the derivative of y? dy dx, all over low squared, y2. And again, this is equal to your second derivative of y with respect to x. Okay? So, but wait a second, I don't want dy dx in there. I want to put this in terms of y. But what was dy dx? Well, dy dx is this x squared over y, right? That's what it is right here. So why don't I just go ahead and I can replace that by saying, I can say that's all equal to 2xy minus x squared times x squared over y all over y squared. And in the interest of time, I'm not going to algebraically manipulate it. I'm just going to say, here it is. That's how you do it. The big key there is once you take your second derivative, you're going to probably have some dy dx's laying around, and you have to input in what your first derivative was. Okay? Whew! That was a lot to take in. Hopefully everything is okay. I'm going to come over here, and we're going to say, boom, there's your homework. It seems like a lot. It's a little bit. Okay, it's a fast turnaround. We only have one day with this. Okay, you're going to have a new section on the next day. Talk to you later. Bye.